everyone, and welcome to Network Playroom. Today we're continuing with OSPF topics. In my last video, I covered the OSPF parameter checks in detail. We investigated the OSPF parameters that must match between two routers for them to become neighbors or form an adjacency. I left out one part though, the MTU, which is strictly speaking not included in the parameter checks, but it is tightly related to the OSPF adjacency establishment process. So we'll look at that in this video. Now, first of all, the MTU, or maximum transmission unit, is the size in bytes of the largest IP datagram that can be sent out the associated interface without fragmentation. Now, the MTU must be equal for the DD packets to be successfully processed between neighbors. If the MTU values are not equal, the routers will not go beyond the xstart state and the adjacency will fail. So let's see how all of that looks like on the command line. I'll use the same evenG lab as I have in my previous videos. This is a very simple topology consisting of 4 routers, and I've actually turned on only 2, which we'll use for the purposes of this video. So let's jump on the command line. Go on R1 here. So right now, both routers have been configured with basic OSPF configuration, and they are fully adjacent. And we can verify that quickly. So show IP OSPF neighbor. You can see that they are fully adjacent. We can even run the same command on R2. Show IP OSPF neighbor. There we go. Now let me go back to R1. Now actually, before I enable any debugs that would give us more detailed information, let's break the adjacency by changing the MTU on one side and see how the problem presents itself in the show command output and possible log messages we'll get. So again, the routers are in the full state right now, which means that they have exchanged LSAs, the databases have been synchronized, and they are fully adjacent. Great, so now let's break it. So we'll change the MTU value on one side, which will cause the adjacency establishment process to fail. The routers will not surpass the xstart state and eventually go down. By the way, I'll pause the recording where necessary because some of these events take a while to occur, so I don't want to keep the recording running and having you wait till like 2-3 minutes for something to happen. Okay, let's go. So before we configure the MTU value, let's see what it is now. So we can check that by using the show IP interface command. And right here you can see that the MTU is 1500 bytes. Note that we're looking at, and next I'm going to manipulate the IP MTU. This would only affect IP version 4. If we were to configure OSPF for IP version 6, which I might actually show you later on, so stick around until the end to find out, the adjacency would not be affected. By the way, we could change something like the system MTU or the interface MTU, but we'll stick to IP MTU for this video. Actually, I'm not even sure if the virtual environment supports those commands, so that's another reason to use IP MTU. So moving on, let's go ahead and change the IP MTU value on R1. For that, we have to go under the interface. So conf t interface gig 0/0, and we'll do IP MTU 1300 bytes, for example, like so. Okay, let's get out of config mode. And let's apply the show IP interface command again to verify that the MTU value has actually changed. Okay, here we go. Now it's 1300 bytes. All right. Now, let's start the OSPF process, so the adjacency establishment process will start from the beginning. And then let's watch what happens. So we can do clear IP OSPF process. Reset all OSPF processes. The default is no, so we'll type yes. Let's go. Let's look at the show IP OSPF neighbor status quickly. So you can see that they are in the xstart state. Okay, this is taking awfully long. We should have received a log message stating that the neighbor status has gone from xstart to down. So I'm not sure why it's taking several minutes. So let's run the show IP OSPF neighbor command again to see what's going on. They are still in the xstart state, so we'll just wait some more time. Okay, finally, there is that log message that I was waiting for. Now, if you look at the timestamps here, so we reset the OSPF process at this time, so 9:53, and look at over here, when we got this log message is 9:58. So that took about 5 minutes for the OSPF state to go from xstart to down. Now again, I have not enabled any debugs yet, so let's see what information we can get in the logs and show commands. Now you can see that it is quite difficult to detect and identify the problem from the information we have available currently. The output does not clearly state that there is an MTU mismatch. For example, if OSPF detects duplicate router IDs, it'll clearly tell you. You will see a log message indicating that directly. The MTU problem is not so evident. The only clue we get here is the from xstart to down, neighbor down, too many retransmissions, which is referring to the DBD packets being sent too many times. So let's look at the neighbor state again out of curiosity. It should be down right now. No, it has restarted the OSPF process, so it's going to go through the same thing, and then eventually we're going to get another log message stating that the neighbor state has gone down. We'll let that run there for now while we discuss a couple of things. And actually, just when I said that, we got that log message, so now the neighbor state should be down. Let's have a look. There we go. Alright, so why does this happen? So the routers exchange their MTU value in the DBD packets when the OSPF adjacency is initialized. If the MTU field in the database description packet indicates an IP datagram size that is larger than the router can accept on the receiving interface without fragmentation, the database description packet is rejected. In other words, R1 is receiving DBD packets from R2 which have too large an MTU value. R1 has an MTU of 1300 bytes and R2 has the default MTU of 1500 bytes. Therefore, R1 is rejecting the DBD packets. Now, the DBD packets are retransmitted continuously until the OSPF adjacency is eventually torn down. And you can see this from the log message, which stated that there were too many retransmissions. So R2 is sending the DBD packets, but it's not getting anything back from R1 because R1 is rejecting the DBD packets due to the MTU mismatch. Let's actually quickly see what's going on R2's side, because we've only focused on R1. So let's see over here. So you can see the same log messages essentially. So again here, from xstart to down, neighbor down, too many retransmissions. But not much else here. Let's wake her up. So if we look at the show IP interface, you can see that here is still the default MTU value. Show IP OSPF neighbor. We're in the xstart state again, so it's restarted the process from the beginning. It's trying to establish the OSPF adjacency. So it's just going to loop through this whole thing, never going beyond the xstart state and then falling back to the down state. All right, now let's enable debugs and clear the OSPF process again to check if we get any more information about the problem. So we'll do it here first. Debug IP OSPF adjacency. Okay, we'll go back to R1. Let's do the same thing here. Okay, so let's clear the OSPF process again. Clear IP OSPF process. Yes. Let's go. We'll let that run for a while again. I'll continue the recording when there's something to look at. Okay, now we have something to look at, so let me disable the debugs. You all. We'll do the same here. Okay, let's go back to R1. And let's run the show IP OSPF neighbor command just to see where we are. Looks like the process has started again. We don't have to care about that, so let's look at the debug output and see what we can find there. Okay, so here we go. On this lines right here, you can see that the problem is pretty clear. Neighbor has a larger interface MTU. And here it actually states the value as well. So this is the MTU value that was received from R2. So if we jump to R2, we should have similar output. So right here, received the DBD from R1. The MTU is 1300 bytes, and neighbor R1 has smaller interface MTU. So now it's clear that the MTU values are mismatched. And actually you can see here that R2 is trying to resend the DBD packets quite a few times, 25. So killing neighbor R1 due to excessive transmissions or retransmissions. And 25 is indicated in the brackets. And you can see that here as well. It's keeping track of the DBD packets that it's sending. Okay, so let's recap what we've learned so far. So OSPF checks if the neighbors are using the same MTU on a common interface. This check is performed when the neighbors exchange DBD packets. If the received MTU in the DBD packet is larger than the MTU configured on the incoming interface, OSPF adjacency will not be established. So in other words, this entire thing is controlled by a single check to verify if the MTU values match. Well, this check can be disabled. And this is done with the IP OSPF mtu-ignore interface command. This command disables the MTU mismatch detection on received DBD packets. So let's try that. Let's go on R1. So we'll go under the interface and then type the command IP OSPF mtu-ignore, like so. And let's see what happens. So you can see that the OSPF adjacency immediately comes up and the neighbors are in the full state. So let's have a look at that. Right there, they are in the full state. We can check it on R2 as well. Show IP OSPF neighbor. Okay. Now, note that using this command only masks or literally ignores the problem, like it actually says in the command, IP OSPF MTU ignore. The problem is still there, although the MTU mismatch is ignored and the OSPF adjacency is established, it can still create serious consequences. INE has written a great blog post about this. I'll leave a link in the description. In short, the LSA exchange process can still fail and the databases will not be synchronized. Basically, R1 would not be able to receive packets from R2 that exceed the MTU of 1300 bytes, which we've configured under the interface. So this becomes a problem, for example, if R2 connects to many networks, the router LSA can become large, exceeding the MTU of R1. Then R1 cannot accept packets that exceed its MTU, which means the LSUs are never received and therefore the routes are never learned. Further, eventually the adjacency between R1 and R2 would be torn down because R2 would never receive LSACs to the LSUs that it sent to R1. So we can actually test this by issuing an extended ping. I don't want to start creating hundreds of loopback interfaces on R2 that would generate a huge router LSA, so we'll just try to demonstrate it with the ping command. So let's jump on R2. Now normally if we ping R1, that's gonna work no problem. However, if we send a packet that exceeds the MTU, it's not gonna work. So let's try that. We'll trigger the extended ping with the ping command. Protocol IP, yes. The target IP address is R1. Yeah, we'll do 5 packets. Datagram size, we'll set that higher than the MTU on R1, which is 1300 bytes, so let's say 1400 bytes. Timeout, let's say 1 second. Extended commands, yes. We don't need that. We don't need to change the source. No. Now here's the important part. Set DF bit in IP header. So the DF bit stands for don't fragment. So this is exactly what we want. We want to send the full 1400 byte packet and not fragment it. So we'll do yes. No. Yeah, we don't need any of this. No. So now you can see the ping fails. So this is exactly what would happen if R2 sent OSPF packets that are too large for R1 to receive. R1 would reject them. In that case, it would not learn the LSAs and it could not install the routes to the routing table, and then obviously routing would fail as well. So this behavior is non-deterministic and very problematic. If you use the IP OSPF MTU ignore command, everything may appear to work as long as no packets exceed the MTU size. As soon as packets that are too large are sent, a cascading problem will occur. So first, the LSAs will not be received, and eventually the whole adjacency will actually be torn down. And this happens because R2 would never receive LSACs to the LSUs that it sent to R1. So eventually it's gonna remove the adjacency. So let's check that again. Show IP OSPF neighbor. So right now it looks like everything is fine, but there's actually a big underlying problem. So you need to be very careful with the IP OSPF MTU ignore command. Now the proper solution in all cases is to configure the correct MTU on the interface. Do not use any gimmicks to allow the initial adjacency to come up by ignoring the MTU sizes. As you've seen, it can be very difficult to troubleshoot this problem from the symptoms. And the symptoms may not actually appear until a critical moment. So again, be very careful with this command. Now, in summary, here are the most important takeaways from this video. Number 1, OSPF performs a check to verify if the MTU values match between neighbors on a common interface. Number 2, This check is performed when the neighbors exchange DBD packets. If the received MTU in the DBD packets is larger than the MTU configured on the incoming interface, OSPF adjacency will not be established. Number 3. This check can be disabled with the IP OSPF MTU ignore command. Number 4. The proper solution is to configure the correct MTU on the interfaces. Now, if you want, you can end the video here, but if you're interested, I'll cover a couple of more things here. So first, let's jump to Wireshark and look at a packet capture right here. So once again, I have the OSPF broadcast adjacencies packet capture from packetlife.net open here. I'll leave a link in the description so you can download this yourself if you want to take a look at it in more detail. So let's find the DBD packet and see how OSPF checks the MTU value. So I can see that there's one right here. So we'll open the OSPF packet. We don't really need the header actually, so we'll go to this part. Let me adjust this slightly. So right here, you can see this field that includes the MTU value. So that's how the router would check whether the MTU values match. So it's going to look at the value in this field in a received DBD packet and compare it to its own MTU value configured on the interface. Okay, then let's go back to R1. All right, let's wake it up. So let me actually remove the IP OSPF MTU ignore command, and then we'll break the adjacency again, and then I'll show you that it does not affect IP version 6 OSPF. Okay, so conf t, and then interface, no IP OSPF MTU ignore. There we go. So the neighbor adjacency has gone down. Let's have a look. All right, they're in the xstart state again. So you can actually see the difference here. If we do show IP OSPF, interface. So again, we can see the MTU over here, 1300 bytes. And let's try IP version 6. Actually, I'm not sure if this is going to work just yet. Yeah, because we don't have IP version 6 configured. So let's do that. So first of all, let's enable IP version 6 unicast routing. This command is very easy to forget, by the way. And then let's go under the interface again. And we'll type an IP version 6 address. Something very simple. Like so. Okay, let's see. So if we run that command again, there we go. So you can see that the MTU is not affected. So let's go on R2 and configure an IP address there as well. IP version 6 address. I can't type apparently. And let's do the unicast routing command as well, because I'm gonna enable OSPF soon. Okay, so now we should be able to ping between R1 and R2 using the IP version 6 addresses. Let's try that. Ping IP version 6. There we go. Now, without explaining the configuration in any way, I'll simply enable OSPF for IP version 6 to demonstrate that the adjacency for IP version 6 will come up while the adjacency for IP version 4 will remain down. So I'm not going to go into detail or describe the configuration I'll apply here. I just want to make OSPF work for IP version 6. Okay, let's go. So let's configure the OSPF process first. So IP version 6, router OSPF. We can use the same process ID, it doesn't matter. And then we'll configure the router ID. All right. Then we'll go under the interface. And we'll put this interface in area 0. IP version 6, OSPF, process ID, area 0. Like so. Let me copy this command so I can use it on R1. Okay. So let's give R1 the router ID as well. And then let's go under the interface and apply the same command that I copied, like so. And let's see what happens. Okay, so we just got the log message. So it went from loading to full. So R1 and R2 are adjacent for IP version 6. If you notice here, OSPF version 3, that's for IP version 6. So we can check that with show IP version 6 OSPF neighbor, like that. And if we do show IP OSPF neighbor, so IP is for IP version 4, you can see that it's still down, or actually in the Xstart state right now, but it will go down again. So let's run the same commands on R2. Show IP version 6 OSPF neighbor, and then show IP OSPF neighbor. So you can see that changing the IP MTU value did not affect IP version 6. The routers were able to establish an OSPF adjacency using IP version 6, but not IP version 4, because there is still that MTU mismatch. Okay, let's go back to R1 and quickly just fix that. So interface gig 0/0, no IP MTU, so it's gonna go back to the default. Show IP interface. You can see it's 1500 bytes again. And we should see the neighbors go to the full state. And I think they already did. Let's just verify that. Show IP OSPF neighbor. Great, and then we'll do the same with IP version 6. So now both adjacencies are up. Like so. Alright, that concludes this video about OSPF MTU Mismatch. Hope you learned something new or have a better understanding of how the process works. Thank you for watching, and I'll see you next time.